Welcome back everyone. Let us start with lecture 1. Let us first look at the objective of this course. So the objective is to understand symmetry present in molecules and correlate its role in chemistry. So let us see how to do that. So the course has two aspects. One is symmetry, another is group theory, right? Now, symmetry, as we know, it is present everywhere around us. It is present in nature. It is created by nature. So, for example, uh, let's look at the cross section of okra, the vegetable, or it's also called as ladyfinger. You must have seen that it is pentagon in shape, and then nice five circles or five small pentagons arranged inside, right? So there is a lot of symmetry going on in there. Then you can also see the differences in flowers with four petals versus flowers with five petals, right? So our brain immediately tells us that this flower is different from another. So we have been coded with the information that symmetry is present out there. Now, what we are going to do in this course is we are going to tap that information and we'll try to visualize symmetry in molecules. Okay, and then we'll try to group molecules based on symmetry. Once we do that, we will try to combine the rules of group theory with the symmetry, and then we will try to predict physical properties or explain physical properties of molecules. Now, what is this group theory? Group theory is a mathematical concept of grouping things. This is based on certain set of rules, and we will all see what the rules are to group things based on certain properties. Okay, so let us look at, let us move forward, and let's actually first start with what we know. So let's try to see the symmetry in mathematical functions. So we are well aware of what is a even function and what is an odd function, right? So we'll be using this concept of even function and odd function to uh, to be able to say or comment about symmetry in wave functions and operators, which are mathematical functions. So let us try to understand symmetry in wave functions and operators and see if we can solve any problem using it. Okay. So in certain areas of chemistry, you will be encountered with specifically spectroscopy. So you will be encountered with something called as transition dipole. Do not worry about it. as of now, what is it? We'll explain it later. So transition dipole moment integral, which is denoted by I and can be written as psi I uh, operator psi j d tau. Now let's say a lot depends on whether I goes to 0 or I does not go to 0. And let's say if we can apply symmetry rules or symmetry in mathematical functions to be able to say whether I is going to be 0 or not for a particular set of operators and wave functions. So can we do that? So let us look at how to do that. So let's say if I have a corollary based on rules of symmetry which says that if operator commutes with parity operator, P. So what is parity operator? We will come to that. And psi I slash psi j is even and other one is odd, then I goes to 0. So basically it is dealing with two conditions. One is if O commutes with parity operator. Second condition is one of this function has to be even and the other one is odd. Then I goes to 0. If both are even or both are odd, then we can say that I does not go to 0. But first it has to fulfill the condition that O has to commute with parity operator. So now let us look at first what is a parity operator. So parity operator, it is denoted by P on any function inverts the sign of the variable. So if it's a function in one variable, it will be P on fx will give you P of minus of fx. If it's a function in, let's say, three variables, all three variables will have inverted sign, x minus y minus z. Okay, so it's like flipping a function through origin. So it's very clear, right? Now let's say if we apply parity on different type of functions like even functions. So even function f of x is equal to f of minus x. So if we apply parity on even function, it will be f of minus x, which will be f of x, right? Because for even function, these two terms are equal. So we can say here that f of x is symmetric with respect to parity. Now let's see what happens if we apply parity on odd function. So let us consider an odd function gx. Okay. So definition of odd function tells you that g of x is equal to negative of g of negative x, right? Now let's say if we apply parity on g of x, what we will get is g of minus x, and in turn we'll get minus of gx. So if we get this kind of situation, we say that gx is antisymmetric with respect to parity. Now in certain conditions, the function can be neither uh, even nor odd, right? It is not necessary. So for example, let's say if we take an example of fx is equal to e to the power minus ax. Now what happens if you apply f of minus x? You get e to the power ax, which is not equal to f of x, which is not equal to minus of fx. So in this case, if we apply parity on e to the power minus ax, we will get e to the power ax, which is neither fx nor minus of fx. So we can say that this particular function is asymmetric with respect to parity. This should be clear, right? This should be easy to grasp. Okay. So now let's come back to the first condition. So the first condition in the corollary says if operator commutes with parity. So what do you mean by commutation? So commutation is written in mathematics as OP comma with square brackets. It means mathematically OP minus PO. Okay. So we have to calculate this, and if this thing goes to 0, we say O commutes with P parity. If this thing does not go to 0, we say O does not commute with parity. Okay. So to be able to calculate this, we need to assume certain operator. So let's assume d by dx, and we also have to have some sort of a function. So let us assume a function as x cube. Now let's calculate the first part, this part, and then we'll calculate this part. Okay. So OP will be is equal to d by dx. Let us write the parity and the operator and the function x cube. Now whatever function comes at the right side will operate first. Okay, so in this case, or whatever operator comes on the right side will operate first. So in this case, the first will be, this will be the first, and this will be the second operation. So parity, we all know by definition, x cube, x has to be replaced with minus x, which will give you minus x cube, right? So d by dx minus x whole cube, this will be minus, can come out, d by dx of x cube, and first derivative of x cube will be 3x square. We have negative sign out, so 3x square, right? Now let us calculate PO. So in this case, P d by dx x cube. So now let's see, this will be your first operation and this will be your second operation. Okay. So first operation, derivative of x cube, which will be 3x square, and we have parity on this. Now if you replace x with minus x to apply parity, so we will get minus x square, which is equal to 3x square. So notice that these two terms are not same, right? So that means OP minus PO is not equal to 0, right? So O does not commute with P. Okay. So our first condition of corollary is not fulfilled here. So let us now look at another example. Let's take O as second derivative, d square by dx square. Let us keep the function as x cube. You can choose different functions, combination of different functions and operators to visualize yourself. So now let us calculate again OP of fx. This will be d square by dx square parity x cube. Now parity of x cube we have all seen minus x cube. So minus comes out, d square by dx square x cube. Right? Now first derivative will be 3x square, second derivative will be 6x. So we have negative of 6x. Now let's calculate PO fx. We have parity on d square dx square on x cube. Now second derivative will be 6x within parity. Now x is replaced by minus x because of parity, so what you will get is minus 6x. So notice now that these two terms are same, right? So we can safely say that OP minus PO will be equal to 0. So we can say now O commutes with parity. Okay. So first condition is fulfilled now. Let us let us now set up an integral to see if we get a combination of even and odd function in psi I and psi j. So let's have our transition dipole moment integral as, let's say you have sin x. We know that d square by dx square operator commutes with parity. We have just proved that. Now let's say we have a function e to the power minus x square dx. Now we know that this thing, so by looking at it, if we can solve it, it will be really cool, right? It looks a dreadful integral to solve, but let's see what are the symmetry rules which says. So OP commutation is 0, so that means O commutes with P. Now this is an even function or odd function? This is an odd function, right? Now this is a even function. So all the conditions of the corollary are fulfilled. That means we can safely say that this particular integral goes to 0. Okay. So very easy. Now do it as a home exercise. Let us set up an integral with I is equal to cosine x d square by dx square e to the power minus ax dx. Okay. Now we all know already that this thing d square by dx square operator commutes. So this thing is already clear, that operator commutes with parity. Now try to identify whether this is an even function or odd function. Do a little exercise. Try to identify if this is an even function or odd function. And now based on symmetry rules, can we say if I is equal to 0, I is not equal to 0? or problem cannot be solved based on symmetry or symmetry arguments. Okay, so try to do it and come back with answers, or contact me for answers if you have any difficulties. Okay, that's all for today. We'll In the next video we will look at symmetry elements and symmetry operations. Thank you.